Good morning students. Today we are going to discuss about one-dimensional wave equation. Before going to the diagram, I would like to give some explanation. The derivation part. First of all, we will consider a small transverse vibration of an elastic string of length T1, which is stressed at the 2 points origin and A. In the equilibrium position, 0A or OA as the x-axis and lined through the origin 0 and perpendicular to the x-axis as the y-axis. Let the P and Q be the 2 points on the string. Let alpha and beta be the angles at P and Q, and let T1, T2 be the tension towards the points P and Q, since if there is no motion, T1 cos alpha is equal to T2 cos beta is equals to capital T. Let's call this as equation number 1. And before going for the explanation further, let me explain to you the diagram. Here you can look at the diagram. There is a string here and the point P and Q. At the particular points P and Q, there is an angle made that is alpha and then beta. This is T1 and then the T2 OA. We have taken a small distance, that is delta x, and when we take up to Q, it will be x plus delta x. This is T1 and this is T2, and angle made at the point P is alpha, angle made at the point Q is beta, and this is the origin 0, 0, and it is a point y, A. This is the explanation I have given. The 2 points on the string, that is a P and Q be the 2 points on the string. Now you can refer. These are the 2 points on the string. And alpha, beta be the angles at the P and Q. T1 and T2 be the tension towards the points P and Q. So you can see this is T2. It is the tension towards the point Q, and T1 is the tension towards the point P. So these are the two tensions we are having. So let M be the mass where unit length of the string, the mass of element of PQ is maximum. In the vertical transverse direction, the components of T1 and T2 are T1 sin alpha minus T1 sin alpha plus T2 sin beta. And we know by the Newton's second law of motion, that is Newton's second law, we have F is equal to m into A, that is force is equal to mass into acceleration. This is, let's call this as equation number 2. And we have the force as minus T1 sin alpha plus T2 sin beta. That is, in the initial transfer direction, the components of T1, T2 are this one. So the force will be this one. And the mass is m into delta x. And the acceleration is given by dou square u by t square. So we have F is equals to mass into acceleration. Therefore, T2 sin beta minus T1 sin alpha, because the force you can see minus T1 sin alpha plus T2 sin beta, writing the positive term in the beginning. So we get a T2 sin beta minus T1 sin alpha is equals to mass into acceleration, where mass is given by m delta x and acceleration is given by dou square u by dou t square. The same thing, dou square x by dou t square. That's the same thing we have written here also. M dx of this one. And here t sin beta minus t cos beta or sin alpha, and dividing by this T2 and then T1. T2 and T1 can be written as t by cos beta and then t by cos alpha. That is, T2 is t by cos beta and T1 is t by cos alpha. That gives m delta x into dou square u by dou t square. Or sin beta by cos beta, we can write it as tan beta, and here tan alpha. Therefore, it is t tan alpha minus t tan beta is equal to m into Vx dou square u by dou t square. Or tan beta minus tan alpha, here we have t, it can be taken common and then it can be taken to the right hand side. So we get tan beta minus tan alpha is m square by t dou square u by dou t square. Here tan alpha and tan beta are the slopes at the point P and Q. So what do we get is tan alpha is dou u by dou x when x is equals to x, and tan beta is dou u by dou x when x is x plus delta x, because tan beta is the point with a small increment, that is p and q are in a very small distance. Therefore tan alpha is the same thing at the point x, whereas tan beta is at x plus delta x. So the second equation implies dou u by dou x of at x plus delta x minus dou u by dou x of x is equals to m delta x by t into dou square u by dou t square, and dividing by the increment, that is delta x. So we are getting dou u by dou x of x plus delta x minus dou u by dou x of x divided by delta x gives us the right hand side. That is, by taking the limit as delta x tends to 0, we get dou u by dou x. We get the dou u by dou x of x plus delta x minus dou u by dou x of x divided by delta x. That is, by taking the limit as delta x tends to 0, the right hand side remains the same. So what do we get? Dou square u by dou x square is equals to m by t into dou u by dou t square, dou square u by dou t square, or dou square u by dou t square is equal to t by m into dou square u by dou x square, or dou square u by dou t square is equals to c square into this we can take it as c square, that is this one. You can take it as c square, so you will be getting dou square u by dou x square, or this is c square can be replaced as the t by m. So the required equation what we are getting is dou square u by dou t square is c square times of dou square u by dou x square. Actually this is the required equation for a derivation. You can look at the diagram once again. This is the diagram. Sorry. So P and Q, we can see there is a small distance between these two. That is with the delta x as a small change, small incremental value. So this is the point. Now we can get to the equation. Yeah. Yes. Dou square u by dou t square is equal to c square into dou square u by dou x square, where c square is t by m. So that's all. This is the wave equation derivation we have. In the next class I will be explaining about how to do the heat equation derivation.